So let's introduce an important idea. A statement has a definite truth value, and contrary to what you might think, we do not want to prove statements true, because sometimes a statement will be false. Instead, we want to prove true statements. So what happens if we have a statement that we believe to be false? For example, suppose we're given a conditional, if A, then B. However, we have reason to believe it's false. This means the negation is true. Well, every conditional is logically equivalent to a disjunction. And De Morgan's laws tell us that the negation of a disjunction is the conjunction of the negations. And here we have a doubly negated A, so that just becomes A. And so we can prove the conditional false if we can show the conjunction A and not B is true. In other words, if we could show that A and not B are both true. So for example, let's consider the statement, all prime numbers are even. How could you disprove this? Note the statement corresponds to the conditional. If a number is prime, then it is even. This is logically equivalent to the disjunction, a number is not prime, or it's even, and our negation, a number is prime and not even. But we know numbers that are prime and not even, so the negation is a true statement, which means the original statement was false. Note that we proved a conditional false by presenting a specific example. The example showed the negation to be true, and we only needed one example to do so. We say that we have presented a counterexample to the claim. So let's consider the claim, all Glerbies are not Fromulus. What would a counterexample be? So again, first note that this is the conditional. If something is Glerby, then it is not Fromulus. Now, it might be a little easier to figure these things out using our symbolic notation, so writing this in logical notation, the original statement is Glerby, then Fromulus, and the negation will be the negation of a disjunction, which will be the conjunction of the negations. And so the negation is something is Glerby and Fromulus. So if we could find something that's Glerby and Fromulus, that would be a counterexample. Now, you might wonder why we're allowed to prove by counterexample, but not by example. And this is most obvious if we rewrite our statement using quantifiers. So a statement like all prime numbers are even is. Remember, we can negate a quantified statement by changing the quantifiers and negating the statement. So that becomes and since this is a there exists, this means this statement would be true if we could find a prime that is not even, and we can. So finding that single example satisfies the requirement that there exists, and so we only need a single counterexample. What about statements that claim something exists? Some even numbers are prime. Since this is a sum claim, we can prove it true by finding an even number that is prime. But what if we can't find that number? So consider the statement, some odd numbers are perfect. Now, so far no one's found any, so it's believed to be false. So what would have to be proven to show that this is in fact false? Note that this is a sum statement, so it begins with an existential quantifier. If we let P be the set of perfect numbers and O the set of odd numbers, then we have there is some perfect number that's in the set of odd numbers. Could we find this statement false by finding a counterexample? In other words, does the existence of even perfect numbers disprove the claim that there are odd perfect numbers? Let's rewrite it using quantifiers and find out. The negation of our statement will be since the negation begins with a universal quantifier, it's equivalent to a conditional. If x is perfect, then x is not odd. And what this means is that proving the original statement false cannot be done by finding a counterexample. Instead, we have to prove a conditional to be true.